Chapter 1, Functions, Relations, Interval Notation, and Compound Inequalities. Quite a long chapter, quite a bit packed into it. And we start out with something that's sort of abstract. We've dealt with it, but we haven't really defined it. And that's the idea of a relation and a function. We start out talking about what a relation is, and the workbook gives us a definition, a couple of them actually, and then they give us some examples below beside the starred comment. Definition 1, rule of correspondence between two sets. Definition 2, a set of ordered pairs. And these are really sort of two different formats that you can see a relation expressed. So if we look at our examples, what we have here is 1, 2, 3, 4. Okay, 4 examples of what a relation is. So the first one is a rule. So we'll write that out to the side. To each person correspond to that person his or her pets. So if we were to sort of sketch sort of a diagram as far as this first relation goes, we could say just make up some people, maybe Mike, Sarah, and Tim, and then the name of his or her pets. Maybe the pets' names were I don't know, Tiny. What's the dog name? Fetch, and I don't know, Cujo. But if we were going to sketch this out, then we would just say maybe Mike has a pet named Tiny, and Mike also has a pet named Fetch. Sarah has a pet named Fetch, and then maybe Tim has a pet whose name is Cujo, and also has a pet named Fetch. So we're taking the people and their names and assigning it to the names of their pets. Alright, but it's sort of it's a verbal rule. It's written out in words. Number 2 is ordered pairs. Okay, this is the first ordered pair in this relation. It is assigning 1 to 2. Okay, and so ordered pairs are designated with open and closed parentheses, and there's a pair of numbers inside. So one assignment is 1 to 2. Another assignment is 2 is assigned to 3, and 3 is assigned to 4, 4 is assigned to 5, and so on. And so this is just another way to express a relation. And then 3, we're given another rule, and 4, we're given another relation in the form of an ordered pair. Okay, so those are some examples of relations. We want to take that definition a step further and define what's called a function. And so the workbook tells us that it's a relation. Okay, it shares the same characteristics that we've already mentioned, except there's sort of one extra detail for a relation to be a function. It says each element in the first set corresponds to exactly one element in the second set. So up here we said that this little diagram, so up here at the top, this diagram that we drew out with the arrows, this is a relation, but the way I assigned the people's names to the pet names causes it not to be a function, and that's because Mike is an element in the first set, and Tiny and Fetch are elements in the second set. Well, Mike is assigned to 2 different pet names. Likewise, Tim is also assigned to 2 different pet names. So this rules out this little relation in as far as being a function. Number 2 is just giving us a definition of a function in terms of ordered pairs. It says no two ordered pairs having the same first element have different second elements. And so if we look up here at 4 and we talk about why is this relation not a function, then we would say Bulldog is assigned to Star City, and Bulldog in each case, this is our first ordered pair here, and this is our second ordered pair. There's 2 ordered pairs in this relation, and in both of them, Bulldog is assigned to a different second element. Okay, it's assigned to Star City and it's assigned to LA Tech. So this number 4 is a relation, but it's not a function. Okay, a first element is assigned to more than one second element. So down below, example 1 asks us to determine which of any of the relations listed above are functions. And if you look back up at the top, we were given the example of a person to his pets, and we say that is not a function because a person could have more than 2 pets. So 1 from up above is a relation but not a function. 2, if we go back up the page and we look, we see ordered pairs, and so what we want to do is look for an ordered pair that basically has a first element repeat. And if you look at it closely, the first elements are 1, 2, 3, 4, 5, and we don't see any of those twice as a first element. One thing to note here for this relation is that there is an ellipsis on the end of it, and that means there are additional ordered pairs in this relation, not just what we see written. And so another thing that this ellipse sometimes implies is that there's a pattern being followed by the ordered pairs given. And so if you look, they're just assigning consecutive numbers to one another. 1's assigned to 2, 2 is assigned to 3, 3 is assigned to 4, and so if we wanted to continue this relation, we would say 6 is assigned to 7, 7 is assigned to 8, and it would continue that pattern indefinitely. So when you look at this, you shouldn't think there are only 1, 2, 3, 4, 5 ordered pairs in this relation, because you have this ellipsis here. Now, with that being said, this relation is also a function because none of these first elements repeat. They're only assigned to one second element. So at the bottom, 2, we say it is a function. No first element repeats. 3, for each UAM student record his or her GPA. Well, this would be a function because each student, unless there's an error, and we don't really consider that errors and whatnot, or duplicate students listed twice. We just consider this to be a function because each UAM student should only have one GPA. Okay, you don't have 2 different GPAs. 4, we've already talked about this one, and what we said was Bulldog was assigned to 2 different cities, 2 different schools, and Bulldog was the first element, and so with it being assigned to 2 different second elements, 4 was not a function. Okay, so on the next page, 2, 3, and 4 were asked to give, to make up our own examples of what would be and wouldn't be a function. 2 says, give a specific example of a relation that is not a function. and I simply wrote out a rule that says a student correspond to their books. Some students may only have one book, but it only takes one student to have more than one book, and that relation is not a function. Okay. At the same time, if you couldn't think of a clever rule to write out, then you could just make up a set of ordered pairs, such as 1, 2, and maybe 2, 3. But then, and if we do not want this to be a function, only a relation, all we have to do is take one of the first elements that we've already used, for instance 2, and assign it to a different second element, for instance 4. And so this would be a relation. We have a set of ordered pairs, but it would not be a function because 2 is assigned to 3 and 4. Example 3 says give a specific example of a relation that is a function. So I made up a rule, a person to their mouth. Okay, every person is only going to have one mouth, and I guess in that sense we're lucky. But you could, instead of mouth, you could say one nose or any other body part where a person normally only has one. So here's a verbal rule for a relation that is a function. And again, if you couldn't think of something to write out in words like a rule, you can just write out a set of ordered pairs. We could assign, instead of numbers, we could assign shapes to letters. And we could make this as long or as short as we wanted to. So triangle to the letter T, a square to the letter S, and then finally we could assign a circle to the letter C. And we could stop it there before we ruined our relation. The way it's written now is it's a function, because triangle is a first element. It's not repeated. We use a square and a circle. And neither are the other two first elements repeated. We only use square once, and we only use the circle once. Okay, 4, give a specific example of a function that is not a relation. This is just sort of a trick question because by definition, if you have a function, then you automatically have a relation. Okay. This may seem kind of odd, all this talk about relations and functions, but you've actually already seen a lot of functions, okay, even if you've only taken intro. One type of function that you've seen would just be a linear equation, okay, for instance, and I could make up 1,000, but I'll just make up one. Let's say y equals 2x plus 1. Alright, this is a function, okay, because it takes an x value and assigns it to a y, and every x, every real number that you can think of that you place, put in the place of x, is only assigned to one y, okay. And so we want to give the first set and the second set that we've been talking about, we want to give them names. And so we're given two terms here, domain and range, and the definitions are given to us. It says the domain of a relation is the set that you're going from. And so when we were graphing these lines in intro, what we would do is we would pick a number for x and we would put it in our equation, and we would calculate y, and in this case, if x was 1, we would get 3 for y. So 1 is assigned to 3. We're going from x and we're going to y. So the domain are the x values that we use in this table here. And we could use other ones beside 1. We could put a 2 here, and then we could calculate 2 times 2 plus 1, and we get a 5. So 2 is assigned to 5. And we could do this indefinitely. But the point here is that the domain are the numbers, or the set of numbers, or just it could be other things other than numbers, like we saw on the first page of the chapter. But it's the set that we're going from, and then the range is the set that we're going to. So for my example of y equals 2x plus 1, my range here would be the y values that I calculated. In this case, I only calculated 2, 3, and 5, but there are others, okay, and they're based off of this equation. Okay, so domain's the first set, range is the second set, or you could think of the domain as being the x and the range as being the y. What we have here is a typical diagram that pops up when you're talking about functions and relations, and this can be referred to as an arrow diagram. Okay, so example 5, we're given our previous examples of relations, and we're asked to find now the domain and range. So one of the first relations that we talked about was to each UAM student his or her GPA. In this case, we're going from the UAM student to their GPA. So domain is the student, range is the GPA. Example 6, we're given a set of ordered pairs. Okay, and anytime you hear the word set in algebra, it's usually followed by, or a lot of times can be followed by some brackets, squiggly brackets. Okay, and inside the brackets we have our elements of our set. So in this case, inside of our set, there are ordered pairs. Okay, 1, 2, and then a third ordered pair. So we recognize this is a relation, and for the domain, we simply want to pluck out the first element of each ordered pair because it is an element of our domain. So Weevil and Bulldog, and we only write Bulldog once. Okay, it is repeated, but these are the elements of our domain, and then for the range we just pluck out the second part of each pair. So UAM, Star City, and then finally LA Tech. Example 7, we're shown sort of, I guess, a set of ordered pairs. 1's assigned to 1, 2 to 4, 3 to 9, 4 to 16, and there is a pattern with the numbers. And we're told, using these ellipses, that there's more ordered pairs. They keep going. They don't just stop at 4, 16. Okay. So questions below, is the relation a function? All we have to do for the ordered pairs is check the first element. 1 is the first element of this ordered pair. Does it repeat in any of the other ordered pairs? We go from 1, and then there's a 2, a 3, and a 4. Alright, 1 does not repeat in any of the other ones. 2 is also a first element, and it doesn't repeat. Okay. Likewise, 3 and 4 don't repeat either. These first elements only occur once. Okay. So, since the first elements don't repeat, this is a function. No first element repeats. 2, what is the domain of this relation? We would write 1, 2, 3, 4, and then we could put a dot, 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 because 1, 2, 3, and 4 are not the only elements, because we have this ellipsis here. Tells us that there's more. So 1, 2, 3, and 4, and then we'll put an ellipsis. And for the range, we'll write 1, 4, 9, and 16 with a dot, dot, dot. Okay, domain first, range second part of the ordered pair. 3, give a verbal rule that could be used to relate each element in the domain to its matched element in the range. And this is where we kind of want to look and try to figure out the pattern. Given the first element, how is the second element found? And if you look at the numbers closely, you'll probably realize that the rule is to square the first element to get the second element, or that is to say, to multiply the first element by itself. Okay, here we talk about something that we saw from up above, and you may have saw already at some point during intro, and that is function notation. Okay, this f of x, and that's the way you say it, f of x, this can be confused by an f times x. Okay, they are side by side, but whenever you see this notation, you need to remind yourself that what we're dealing with is the name of a function. Okay, we're given a function a label. So this is function notation. You could see other names for functions or other labels, such as g of x, h of x. You could use any letter for a label, but you need to be careful whenever you see this parentheses with an x inside. What you could be dealing with is function notation, and not just simply the multiplication of two variables. So just to write a few more, you could see m of x or y of x. Okay, and what we're saying here is that there is a function called g, a function called g, and it depends on x. Okay, likewise, h of x, the label or the name of the function is h, and it depends on x. Okay, so in this case, function notation is usually followed by an algebraic expression telling us how to calculate the output based on an input x. Okay, so if the x is replaced with a number such as f of 2, then we're being given instructions to place that 2 to substitute it in for the x variable in the expression to the right. And so that's exactly what we do. We go to the right, we take the expression, and we replace x with a 2. And then what we do is calculate that expression using the order of operations. So 2 squared would be a 4, and then we have an extra 2 in front of it. Negative 2 and 3 will give us a plus 1. 2 times 4 is 8, plus 1 would give us 9. So, in the case of this function notation here, we could write x is the input, and f of x is the output. Okay, so when x is 2, our output f of x equals 9. Alright, f of negative 3, so the next pair that we're going to have in our table, we replace, and I'll sketch that way over here where I have some room. F of negative 3 is equal to 2 times negative 3 squared minus a minus 3 plus 3. Okay, so this first minus was a part of the expression up here. Alright, this second minus was a part of the x that we were given. Okay, it was a part of the number that we're substituting in. So we end up with this minus minus situation here. Minus 3 squared is a positive 9. Minus minus 3 is a plus 3. And then we add 3 more. And we end up with an 18 plus a 6, which is a 24. So, for our function, our input was negative 3 and our output was 24. Alright, this phrase here, the value of f at 0, could be written in function notation by simply writing an f followed by parentheses and a 0 inside. So what they're telling us here, the value of f at 0, they're telling us to put 0 in the place of x, just like we did with the 2 and the negative 3. So that looks like this: 2 times a 0 squared minus a 0 plus a 3. And in this case, the first two terms, they get knocked out by the 0. Okay, a 0 times a 2 or a 0 squared is still 0. So the only thing we're left with is a 3. Alright, so our input here was 0 and our output was 3. Okay, so you could see this with any number, not just 0. We could call this function notation f of negative 3 the value of f at negative 3. Okay, so we can write this out in words just like we can use the function notation. The next one is liable to throw a lot of students off. F of t, and we're given the function in terms of x. You do the same thing that you did with the numbers. You simply take the x and you replace it with a t. And so this is actually one of our favorites because all we do is replace one letter with the other one, and we don't know what number t is, so that's as far as we can go. We basically just have an expression based on a different variable now, t. Okay, so you could say our input was t for our table, and our output is a 2t squared minus t plus 3. And now we, instead of putting a letter, okay, so we've put numbers, we've put a letter, a single letter, and now for this last example, we're given an expression, a t minus 3, a variable and a letter. So we do the same thing as we had before. We replace our x with a t and a minus 3. Make sure you put parentheses around the t minus 3 and then you square it. Then we have minus parentheses t minus 3. So whenever I have to insert a negative or I have to insert an expression in the place of a variable, I always put these parentheses around it. Okay, and then on the end we have a plus 3. Now, this one can be simplified. We don't want to leave it this way. What we want to do is go back and we want to expand this t minus 3 squared, and it will become a t squared minus a 6t plus a 9. And then this minus here, we want to distribute it and get a minus t plus 3 plus 3. Okay. If we take it further and combine like terms, then we would write, we would distribute this 2 now to get rid of the parentheses, and we would have 2t squared minus 12t plus 18, and then we just copy down all this other stuff that was outside the parentheses, minus t, and we could go ahead and add 3 and 3 and get 6. And now finally that all the parentheses are gone, we can combine like terms and write 2t squared. We have a 12, a minus 12, and a minus 1t, making a minus 13t. And then we have an 18 and a 6, and that makes a 24. Okay, so whenever you do have to insert a variable or an expression, you want to try to reduce it to unlike terms. Okay, so we can't combine any terms anymore. This is as far as we can go. So we want to clean it up and simplify it as much as possible. And so to finish our table, our input was t minus 3, and our output was 2t squared minus 13t plus 24. Okay. At the bottom of the page, we have arrow diagram, and it wants us to pick out the domain and range, and then it wants to know if there's a rule that we can write verbally as to how the first element's assigned to the second, and then it asks us, is this relation a function? Alright, so first set is always on the left, second set is always on the right, and so our domain is just simply the numbers or letters or shapes or whatever the elements are inside of this oval. Okay, it doesn't always have to be an oval, it can be some other shape, but this is our first set. So 2, 4, and 6 are the domain of this relation. The range is simply the elements of the second set, and so we have 2, 1, and 0. And is there a rule? Okay. To figure that out, we have to figure out which numbers assigned to which, and so that's usually a lot easier to see if we rewrite this arrow diagram in terms of ordered pairs. And so 2 is assigned to 0, and then 4 is assigned to 2, and finally 6 is assigned to, 4 is assigned to 1. And then 6 is assigned to 2. Okay. What kind of rule could we make out of these assignments? 2 goes to 0, 4 goes to 1, and 6 goes to 2. Well, let's see. If we looked at the difference, then we could say to get 0, we started out and we subtracted 2 from 2 to get the second element. Next, if we took 4 and subtracted 3, we would get the 1. And then finally, if we took 6 and subtracted 4, we would get 2. So, probably kind of hard to write out in words, but we subtract 1 more for every ordered pair that we create. So for instance, if I was to write here 8, then I would go off to the side and say 8 minus, and I've already used 4, so I'd subtract 1 more, a 5, and I'd get a 3. Okay, so 8's assigned to 3. For each successive ordered pair, you could say you add 1 to the second element. Alright, so is this a function? And the answer is yes. Okay, no first element was assigned twice. Okay, alright, and this last one, that's just one that I made up. This did not have an ellipsis or anything, and so the only elements of this relation are 2, 4, and 6 for the domain, and 2, 1, and 0 for the range. Alright, this next section for this chapter is going to try to familiarize us with a few functions that can be written algebraically. And it's very helpful to sort of go through a couple of the standard functions because they just come up so often. And it's good to know a little bit about each one. And since we've talked about or defined domain and range, that's what we'll do with each one of these. And most of them we've seen before. Just like example 10, that's pretty much all we dealt with in intro algebra, linear functions. Okay, and here what we have is the slope-intercept form. Okay, y equals ax plus b, and the only difference being that a is our slope, and usually we use the letter m for the slope. But this is still a function in linear form, and the way you pick up on whether an equation is linear or not is by simply looking at the variables. If you look at the y, its exponent's 1, and then likewise the exponent of the x is also 1. A and b are just coefficients. Okay, they could be any number, positive, negative, rational, and so on. Any number you could think of, but y and x are the variables. So if you're given an equation and the exponents of the y and x are 1, then it is linear. Alright, so out to the side they gave us a specific example of a linear function where a is 2 and b is 1. Alright, this format of equation is called slope-intercept, because the coefficient of the x term is the slope, and the constant term of the equation is the y-intercept. So, to graph this, the first thing we need to do is pinpoint the y-intercept, and we just go to the y-axis and we plot a point at y equals 1. Alright, now if the slope is equal to 2, what we can do is write it as a fraction, 2 over 1, and we interpret the numerator as the rise and the denominator as the run. Okay, rise is up or down, run is left or right. Now, with both of these being positive, that means we're going to go up, and then 1 is positive, that means we're going to go to the right. So we start with our y-intercept, not at the origin, so we have to plot the y-intercept first, and we go up 2, and then we go right 1, and at that point we plot a second point. Alright, and from here on out, if we just keep applying our slope up to right 1, then we'll end up with a bunch of points that fall in a straight line. Okay, so once we find 2 of them, all we really need to do is draw a straight line through the 2, and all of the other points will automatically fall on the line. Okay, so try to draw it as straight as you can, but nobody's perfect. Here is our linear function. So it's a solid line. Okay, there's no gaps in it. And so what is the domain and what is the range? Well, the domain is simply what numbers, sort of a question I guess, what numbers can you use for x? Okay, what numbers can I put in here in the place of x and multiply by 2 and add 1 and actually get a real number back? That's sort of what it's asking. An easier way to answer that question is to look at the graph. Okay, now if we thought of this line as casting a shadow on our x-axis, then it would cover all of these numbers on the left, and then over here to the right, after it crosses the x-axis, it would cover all of these numbers below it. Okay, so you can think of it as casting a shadow, or you could apply what we call the vertical line test. Okay, pick any x that you want and draw a vertical line. It's real simple. Then ask yourself, does that vertical line hit our function? And yes, it does. Okay, pick a different x, draw a vertical line. Does that line hit the function? Yes, it does. Okay, so anywhere that you can draw a vertical line and hit the function, that means that that value of x is in the domain. And so what you see here is that there's really no place that we can draw a vertical line on the x-axis and not hit our red line here, our function. Okay, so that's sort of the logic that you go through when you're trying to figure out what the domain of a function is. And for a linear function, turns out that we can put any number that we want to in the place of x. This linear function continues to infinity to the right and to the left. Okay, likewise, a linear function shadows or covers the entire y-axis. Okay, in the case of the range, you would think of yourself doing a horizontal, I spelled that wrong, I don't know, horizontal line test. Okay, so if we did a couple examples of this, what we're trying to do is there a gap? Vertically, is there a gap? Is there a place where I can draw a horizontal line and not hit the function? Okay, and the answer to that question is no. It doesn't matter where I draw this horizontal line, I'm always going to hit this red curve, no matter where I put it, up, down, So we say our range is from negative to positive infinity. Okay. So to sort of speed things along here, I'm just going to go ahead and quickly work out the next few examples of some different functions that you're going to run into. The next one is a squaring function, y equals x squared. Okay, it has another name. You can call it a parabola. All right. If you sketched a table of values, meaning you draw a table and you label two columns x and y, and then you just started picking x values, 1, 2, 3, positive, negative numbers, and you calculated the y's, okay, negative 1 squared, 0 squared, 1 squared, 2 squared, 3 squared, and so on. Then when you plotted those x and y pairs, you would end up with a function that's pretty much shaped like this. Sort of a U, okay? And in this case, this is what you would plot if you had y equals x squared. Now, this thing can be moved to the left, right, up, or down. It can be flipped upside down. But whenever you see a function that is U-shaped, it's a very good possibility that it could be a y equal x squared. Now, for this particular type of function, the domain spans all x values. You can put in any value that you want to in for x, and you will get a real number back. However, for the range, and that's for this particular example only, y equals x squared, the range in this case would start at 0 and would go to positive infinity. Alright? And if you remember what I said from up above, for the range we perform what's called the horizontal line test. Okay? We just pick random places in our graph and draw horizontal lines. And if you draw any horizontal line below the x-axis, you can't hit the function. None of these lines below the x-axis cross our function. But once you break above the x-axis, we start to hit it. And sometimes we hit it twice. Okay, hit it 2 times. So, what we say is, the range, what kind of outputs can we expect from a squaring function? We can expect any value from 0 to infinity for this specific example, y equals x squared. Cubing function, the x is cubed, it's going to look like this. Maybe a little sharper actually. If you cube 2, you would get 8 way up here, so this is really sharp. Okay, and then if you cube the negative 2, you get a negative 8 somewhere way down here. So it cuts through the origin and then it shoots over here and drops off real quick. Okay, so this is a picture of a typical cubing function, y equals x cubed. Keep in mind that this could be shifted to the left, to the right, up or down, and it could also be flipped upside down. Okay, you could get a cubing function that looks like this. Alright, but in the case of y equals x cubed only, okay, no other numbers on the side with the x, in this case the domain is all real numbers, so we write negative infinity to positive, and then the range, it spans the entire y-axis. So again, all real numbers for both the range and the domain. Okay, so you can write it out in words, or you can put the ordered pair with negative and positive infinity. So practically, what this means to say is we can put any number in that we want, and we can get any number that we want to get out of it out. All right. All right. 13 and 14. How do we determine the domain of a function by using its graph? We call it the vertical line test. How do we find the range? By looking or inspecting the graph of a function. We call that the horizontal line test. Okay, and we're really looking for places where the vertical or the horizontal line do not hit the function. Those values will not be in the range or domain. Okay, so keep in mind this page, page 7, they're laying out a few basic graphs along with their standard formats. For instance, linear, we've got the slope-intercept form, y equals x plus, or y equals ax plus b. Quadratic, or in other words, a parabola. You could say this is a squaring function. So we got the x squared component, and then we can have a coefficient in front of the x squared, and then we can have a constant off to the side. And then we could have a cubing function, and then a few others that we didn't mention specifically up above. Absolute value, okay, these bars. These vertical bars here are absolute value bars. We take the 0 or positive value of the number inside. We have square root. Here's a radical. Okay. And then they give you a little picture of what they generally look like off to the right. Okay. Any of these can be referred to as parent functions whenever a equals 1 and all of the other coefficients are 0. Okay, for the remainder of the chapter, we're going to be talking about some inequalities, and so you need to know how to graph or express inequalities in some sort of format, and there's 3 that we can pick from. They're called interval notation is one. Okay, we can graph them on the number line, or we can write an interval in what's called set notation. And you typically run into these whenever you're dealing with inequalities. So there's 2 types of notations or symbols that you can run into with interval notation, and that would be a bracket or a parentheses. Okay, and then you can mix the 2 together. For one of the numbers in the pair, you can have a bracket and the other a parenthesis. Okay. And what the bracket means is that the number that's next to it is included in the interval, and then for the parentheses it means that the number that is next to it is not included, and whenever we graph it we want to put an open dot in its place. And so I've got a few of these examples worked out. If we were given this as our interval notation, what it's telling us is that we have the numbers, any numbers in between a and b, okay, these numbers that are shaded in the middle, any of these numbers are in the interval, and then with a and b having brackets, A and B are included themselves. And so to show that on a number line, we put in the place of A and B solid dots. And we also want to label our dots with the numbers A and B. Okay. For set notation, one thing you want to notice is that you always start out set notation with the name of the numbers, X, and a bracket and a bar. So bracket, the variable, and a vertical bar. Bracket, variable, and a vertical bar. And then on the end of each set notation, we end it with a closed squiggly bracket. Okay, so this feature is a part of every set notation. Bracket, or squiggly bracket, X, and then a vertical bar. And then, as you can see on the inside, we express the shaded numbers using inequalities. And so here we see that X is a number that is less than, or it could be equal to B, but then it's also to the right or greater than the A or equal to A. Okay, so any of these three in this first row, they represent the same group of numbers. For the second one, we have parentheses with an A and a B, a pair of numbers inside. And that is to communicate that we have any number in between A and B included in our interval, but A and B themselves are not included. So we place open dots in their respective places on the number line. Okay. So only the ones in between get shaded. And now to draw the set notation, we have our bracket, X, bar, and then we express the shaded part of the number line in terms of inequalities. X is in the middle of A and B. So we write X is less than B and greater than A. Okay, so visually it is in between the A and the B, just like visually you see the shaded part between the A and the B on the number line. Now, notice that these inequalities do not have the equal to bar below them. That is because we had open dots here in the places of A and B. Or you could say we were initially given parentheses for both A and B. Alright, so I'll go ahead and work a few other ones out. Make sure you copy down the ones that I did do. We'll look at this one that hasn't been worked yet. Bracket for A, and then it continues all the way out to infinity, positive infinity. So we would do, we would write this on a number line by first drawing a horizontal line. We would locate A, okay, and it could be anywhere. We don't know exactly what number it is, so we just place a tick mark and we label it with an A. And then the A had a bracket beside it. So on the number line, we put a solid dot in the place of A. Now, A is on the left, and so to the right we have infinity. So that means as we go shade to the right beyond A, we shade all the way out to the arrow on the right. That is to say, these numbers never stop. They continue on out to the right to positive infinity. Okay, so we don't need a B that we're referenced to. We just shade to the end of the number line. Alright, to write our set notation, we put a squiggly bracket, an X, and a bar, and then we say X is greater than or equal to A. Equal to bar because we had a bracket, and X is greater because we shaded to the right on the number line. Alright, and one more, we'll work this one out. Okay, from negative infinity to A, and so to represent this with a number line or geometrically, we would locate A. A has a bracket, so again, A would have a solid dot on the number line, and then from A to negative infinity, so we go to the left. We shade from A to the left all the way out to the end of the number line that we've drawn to indicate that this interval continues to negative infinity. Alright, so we're finished with the number line, and now we draw our set notation. Bracket X, vertical bar, and X is less than or equal to A. Okay, so to really get the hang of this, you really need to get on Alex and practice this a few times, and there are some problems. Whether you're using Alex or WebAssign, get plenty of practice with this, and it actually turns out to be pretty simple once you've worked enough of the problems. Bracket is closed dot, parentheses is open dot, negative infinity, shade all the way to the left, positive infinity, shade all the way to the right. Okay, the next page, we get a little practice writing these notations. One of the problems up here at the top, they gave us an example. It's already worked out. This one is already worked out for us. And so is the next one. I've already sort of worked it out. But what's happening here is we're given not the interval notation, but we're given the number line. And so you can see this part of the number line is dark. And at the -7 we have an open dot. And then we skip part of the number line, and then we start at 9 with a solid dot, and then everything beyond that is shaded. Now this is what the workbook gave us. Okay, these parts that are shaded are darker than this part in the middle. So how do we represent this number line using interval and set notation? Okay. Just like the number line is broken up into two separate shaded parts, we have to express this interval in two separate parts using the union symbol. So the part on the left in set notation would be bracket X, vertical bar, and all of those numbers are less than -7. Okay. So this part represents the part on the left. Alright, then we have a gap, and so in our set notation we put a union symbol. Alright, so we can join the two parts together. Then we pick it up with the 9, but we're dealing with set notation, so we put a bracket X, vertical bar. Okay, it's just automatic. And then we say, well, this other shaded part is to the right of 9. So inequality wise, X, which X represents these shaded numbers, X is greater than or equal to 9. And then we close the bracket. We close the set. So we had the equal to bar, because with the 9 it's a solid dot. We had no equal to bar with the 7 because it was an open dot, and that's a -7. Alright, so we had to use this union symbol with the set notation. Likewise, we use the union symbol with the interval notation. So we start at -infinity because the number line shaded all the way out to the left. Okay, there's no stopping point for the shaded part. So we pick it up with -infinity. And the shaded part continues up until we get to -7, and then it stops with an open dot. So for the pair negative infinity, negative 7, we have a parentheses beside the negative 7. We have a gap, so we use a union symbol, and then we pick it back up with 9, and we place a bracket beside the 9 because 9 is included in the interval. It has a solid dot. Beyond 9, we go all the way out to positive infinity. And so this completes our interval notation. Okay, example 16, we're given interval notation and we want to go to the number line or geometric representation. So what you see here is we always start from left to right, and we say we start at the far end of the number line all the way out to the left, and we continue to shade up until we hit the next number, 6. And 6 has a parenthesis, so on our number line we put an open dot at the 6. Then we have union, which means that we stop shading. Okay, we stop shading in the middle. There's a gap, and we do not pick it up back up until we get to 8. Okay, so 8 starts the second part of our interval. It has a bracket, and so there is a solid dot placed at 8, and then beyond 8 all the way out to infinity we shade all the way to the far right of the number line. Okay, so you can visually see what numbers are in our interval. Okay, numbers less than 6, greater than 8, and 6 itself isn't included, but 8 is. And no numbers in between 6 and 8 are included in the interval. Alright, here for 16 we want numbers less than negative 3 but not equal to, so we put an open dot at negative 3 and we shade to the left. Left is less. Then for our second part of the interval we have x is greater than 1, not equal to 1. So again we put an open dot at 1, and now the numbers that are greater than 1 are the numbers that are to the right. So on the number line we shade to the right. And so the numbers that are in the middle, they are left out. Okay, so we'll work this one out. 18, we're not given the simplified versions of the inequalities. Okay, we're required to do a little bit of effort to figure out what numbers are in our interval. So we're given two inequalities. Here's the first one, 2x plus 3 less than or equal to 9. That's our first one, and then we have a second one, 3x minus 1 less than 5. We need to whittle these down, each one separately. So I write 2x plus 3 less than or equal to 9, and I want to get the x by itself. So I subtract 3 from both sides. I divide by 2. And we get x is less than or equal to 3. So now we know exactly which numbers is represented by this particular inequality. It's not clear when you have a lot of numbers grouped around the x. So get the x by itself. Now we have 3x for our second interval, 3x minus 1 less than 5. Get the x by itself. We add 1 to both sides. We divide by 3, And so on one hand we want numbers less than or equal to 3. On the other hand we want numbers less than 2. Now, something that you may have just read over and not paid any attention to is the word and. With the word and, we need to interpret these two intervals using an intersection symbol. Okay? And I remember that intersection is applied when you use the word and, because and has an n in it, and the intersection symbol looks like a lowercase n. So, what the intersection means is that we want numbers that are in both intervals. Easiest way to figure out what numbers we're referring to is to draw these two inequalities on two separate number lines. Draw this a little flatter. And then compare the two. So, x less than 3 is going to go on the top one. It has an equal to sign, so I'll put a solid dot at 3. And I want numbers less than 3, so I shade to the left. I'll put the second inequality on the second number line, and 2 is less than 3, so 2 is going to be over here to the left somewhere in here. I wouldn't want to put it over here because that would mean 2 is greater than 3 in it, and that's just not true. So 2 goes over here to the left, and I do not have an equal to bar for 2, so I put an open dot, and then I want numbers less than 2, and so from 2 I again shade to the left. Alright, and you're not always going to shade in different directions. We shaded both of these from the number to the left. Okay, which numbers are in both intervals? That would be these numbers right here, the numbers that are less than 2. Okay. So 2 itself isn't included because it's not included in this second interval. 2 is included in the top one, but not the bottom one. So we only include numbers that are less than 2. Okay. So this is our interval. Okay. To graph it, it looks like this. 2, shade to the left. Real simple. Just put a 2 there with an open dot and then scribble to the left. Alright. If we wanted to write this in set notation, we would draw a squiggly bracket, an X, and then our inequality x is less than 2. Real simple. If we wanted to write interval notation, we would write from negative infinity, because we shaded all the way to the end on the left, that's where negative infinity is, all the way up into 2, and then 2 is an open dot, so I put a parentheses beside it. Okay, for our next one, we've got 3u minus 1 less than negative 7, and then on the other hand we have 4u minus 5 greater than 7. We need to get both of these broken down to where the u is by itself. Just work on one at a time. Add 1 to both sides for this first one. Divide by 3. And we get u is less than a negative 2. Here is a part of our solution. And then we add 5 to both sides for this other interval. 4u is greater than 12. Divide both sides by 4. U is greater than 3. Okay. And here we're given the intersection. So we want the numbers that are in both. Alright, not just one or the other, but they have to be in both intervals. So Easiest way to figure that out is to draw two number lines on top of each other and locate your reference numbers, -2 and 3. Okay, 2 is negative, so it's going to be on the left. 3 is going to be on the right because it's bigger. And we'll line them up so that we can compare the two number lines more easily. And then u less than -2 I'll put on this first number line. So -2 gets an open dot, and I shade to the left. Okay, u greater than 3, again, open dot, because there is no equal to bar here for the inequality. And we want u numbers greater than 3, so we shade to the right. Well, we want numbers that are in both this shaded part and that shaded part, but there are none. Okay, shaded parts have no overlap. So we write this symbol. We just write a 0 with a slash through it. The interval is an empty set. Okay. You could say there's no solution. There is no number that satisfies both of these inequalities. Okay, example 20. We've got them already worked out for us. Again, we're looking at the intersection. So we'll just go ahead and put them on number lines. We've got our reference numbers 5 and 7. And so for this first inequality, we have equal to 5, so we put a solid dot at 5, and we want numbers greater than 5, so we shade to the right. B, we have x less than 7, no equal to bar, so we put an open dot for 7, and we shade to the left. Left is less. Alright, we want to figure out the intersection of these two intervals. In other words, where do they overlap? Intersection. Well, they intersect right in the middle. Okay, and we leave out 7, but we include 5. Alright, so graphically our solution looks like this. 5, open dot at 7, shade in the middle, and then we want to write it in interval notation, and that would look like this. Solid dot for 5 means we would use a bracket for 5. Open dot for 7 means that we would use a parentheses with 7. And then for set notation, we would write x is a number that is in between 5 and 7. Okay, and visually you write x in the middle of the 5 and 7, and then you put inequalities in between them. And x is less than 7 and greater than or equal to 5. And then we close our bracket. Alright, so we have interval, set, and graph. Okay, so this chapter is getting kind of long. The video is now heading on an hour and 20 minutes. So you may have to break it up. Hopefully you didn't watch it straight through. Hopefully you took a break in between. But these last few, they're already worked out. I'm just going to try to explain a little about each one real quick. Here, we have two inequalities like we did before, but now we have a new word in between there, a new conjunction, or, and that is the union between them. So really we just want to take the two and combine them on the same number line. Alright, we took the first inequality, 2x plus 3 less than or equal to 9, and we whittled it down to an x less than or equal to 3. Then we took the second one, 3x minus 1 less than 5, and we whittled it down to an x less than 2. So, for x less than or equal to 3, we have this top number line shaded to the left, and for x less than 2, we have this bottom one, open dot at 2, shade to the left. Well, we want to include in the final answer over to the side anything that is shaded. Okay, so any number that's shaded, which is to say 3 is shaded, so it gets included in the final solution, and then any number to the left of 3 is shaded, and so we shade those two, and then the bottom number line simply includes ones that were already included in the first interval. So we end up with x less than or equal to 3 for our solution. Alright. So for union, it doesn't have to be in both. It can be in one or the other. Union include all shaded numbers, whether it's in one or the other. Okay, 22's worked out for you. I'll let you maybe look at that yourself and sort of follow it. But 23 isn't worked out, and that's what I'll do with the last part of my video. We already have the inequalities with the x by itself, so we'll write out, we'll graph both of these, A and B, and our reference numbers are 5 and 7. Okay, I'll put A on the top and I'll put B on the bottom, and so A is 5 solid dot because we have the equal to bar, and we want numbers less than 5, so we shade to the left. For B, we want numbers that are less than 7, so we shade to the left of 7 on the bottom number line, and then we have no equal to bar there, so 7 receives an open dot. Now we want the union of the two, so that means any numbers that are in one or the other, any shaded number, and that leaves us with these numbers that are left of the 7. It's just that these numbers to the 5 are sort of double shaded, but nonetheless our solution is open dot 7 shade to the left. Okay, and to write that in interval notation, we would write negative infinity to 7. Both have parentheses, and then for set notation we would write x vertical bar bracket x less than 7 close the set with squiggly bracket. And so that was quite a bit for the first chapter, probably one of the longer chapters in the workbook. They're not all this long, but make sure you get on Alex or WebAssign and get started right away, and try to get plenty of practice with what we covered from chapter 1. Thanks for watching.